Hello, Prof. Joe here. Today we're going to talk about resistance to angular acceleration and this quantity known as the mass moment of inertia. To do that, we're going to first talk about mass. And I'm going to run a little virtual experiment. So here we've got a couple of masses. The one on top, the white one, it's a little bit lighter than the bottom one. You can see it's a little bit smaller. And I'm going to apply a force to both of them. Same force to both body. And we'll see what happens. Okay, as I push both of those, you can see the top one accelerated more quickly. Now, if you're in dynamics class, you're probably not very surprised about that because you already know Newton's second law, that when there's a net force applied, it's going to be directly related to mass times acceleration. Let's go ahead and solve for mass in that equation. Mass is going to be equal to the sum of the force, or the net force, over acceleration. And that is the definition of mass. Mass resists acceleration. You can see the inverse relationship between mass and acceleration. You could say for a given force, a larger mass will have less acceleration. Or for a larger mass, you need more force to get the same acceleration. So mass is resisting acceleration. And we're talking about linear acceleration here, or translation. Okay? So what happens when I take these same two masses and instead of pushing them, having them translate, I apply a moment. I apply a rotational force, a force times a distance, to the bodies. Okay, I'm going to do that. Oh, it didn't work. There we go. Now these both spun around 2 times, and as you can see, the top one got there quicker because the top one was able to have faster angular acceleration. So initially you might think, well, it's the same relationship. The top one is lighter, and so you give it the same torque, it spins faster. But if we do a second experiment where we have 2 large disks, and both of those disks have the same amount of weight on it, so both of these have equal mass. If I spin these 2 disks with the same moment, we have a similar effect where the top one is going more quickly. Why? Because those black dots, which I'm using to represent mass, are closer towards the center of rotation. Whereas in the bottom one, they're further away. Same mass, but we still have this larger resistance to angular acceleration with the bottom object. You've probably seen something similar to this before in figure skating. A figure skater can spin very slowly, and then just by tucking in her arms and legs, all of a sudden spin very quickly. She's having constant angular momentum, but because she's able to change what's called the moment of inertia, she can have a larger angular velocity. Let's see if we can use some equations we already know to explore this idea of moment of inertia. And how we're going to do that is we're going to take this disk that we already pushed around and spun, and we're going to investigate it a little bit further. We're going to zoom in, and we're going to just look at half of it. And we're just going to look at a single mass. And that single mass we're going to call dm, because we're thinking of this as a small piece of mass. And this is a discrete mass in my picture, but you could also think of it as an infinitesimally small piece of a body. That one little piece of mass is going to be at a distance r from its center of rotation. And there's going to be a force acting on it. It's just a small amount of force. We're going to call it dF. Okay? And that force, where's that coming from? Well, if you think of this spinning object as a merry-go-round and the black masses on it as children playing, it would be the merry-go-round pushing their feet to make them spin around. Okay? So let's go ahead and start with Newton's second law. We have that sum of the forces equals mass times acceleration, but because we're using a little piece of force and a little piece of mass, we'll just say that dF is equal to dm times acceleration. Okay, but we know now we're doing spinning, where there's something involving the radius here. Okay, so we're going to turn that force into a moment. We know that force times distance equals a moment, and we know that a force applied at a distance, as we can see here, would create a moment about that center point. So I can multiply the left-hand side of this equation by r, but that would change the equation if I didn't also multiply the right-hand side by r. So I'm going to put an r on both the left hand and the right-hand side, and now the equation is still equal because I did the same to both sides. Okay, the only other thing I'm going to do is say that we know a little bit about angular acceleration and how it relates to linear acceleration. You probably remember the scalar equation that acceleration is equal to alpha r. Okay, so we're going to plug that one in as well. On this side, I'm going to go ahead and combine my r and my f and make that into a moment and say it's a little piece of the total moment. So dm, a little piece of the total moment, is going to be equal to it's going to be equal to r dm, and then I'm going to put in alpha r for a. And you notice that we have two r's there. We're going to combine those, and we're going to say that dm is equal to r squared dm. Now it gets a little confusing. We have two m's here. The capital M means moment. The lowercase m is mass. R squared dm alpha. And then we're going to add up all those little moments by integrating, and add up all those little masses by integrating. Okay. On the left-hand side, we just get that total moment, or the net moment. I'll put a summation sign there just so that we remember that there could be multiple moments happening to a given body. On the right-hand side, we have the integral of r squared dm times alpha. This quantity here is the moment of inertia. And we're going to indicate that by calling it I. So we have a new equation, very similar to Newton's second law, but this equation is for rotational acceleration. The net moment on a body is going to be equal to I alpha. And I is going to be equal to the integral of r squared dm. And there, we've just come up with our own equation for mass moment of inertia. Now let's look into this quantity a little bit more. Okay, so let's explore this quantity that we just came up with, where the net moment applied on an object is going to be equal to the moment of inertia times the angular acceleration. And the moment of inertia is going to be the integral over the entire mass of the object of r squared dm. Okay, so first let's just talk about units. So our r is going to be in units of distance, and it's squared. And then our dm, our integral dm, that's going to be in units of mass. So we expect in the SI system, we'd have kilogram meter squared. Okay. In the English system, AES, we would expect to have slug feet squared. And these units might seem a little strange, but you can see where they come from directly from our equation. We're taking the integral of the entire mass and multiplying it by a distance squared. Got to make sure our values are in these units. The next thing we want to talk about is how we're actually going to calculate this thing. And to do that, we really want to be able to bring in the shape of an object. We have dm now, but we can relate dm to the volume of an object by using density. Okay. So what's density? Well, I'm going to use rho to indicate density. And we know that rho is going to be equal to mass over volume. We are looking at a little tiny piece of mass. I'm going to call that a dm. And of course, I've also got to call that a dv. And then I can solve for rho. Oh, I'm sorry. I can solve for dm. Rho dv is going to be equal to dm. Okay, now I can take that and plug it into our equation. And we'll have that the mass moment of inertia is going to be equal to the integral of r squared rho dv. And we are now integrating over the entire volume of an object. Okay, if that density happens to be consistent throughout the entire volume, we can take it out of the integration, and we would have, this would be equal to rho times the integral over that volume of r squared dv. Okay, another really important thing to note is that all bodies are going to have multiple moments of inertia. The moment of inertia is dependent on the axis that you're calculating it about. Okay? Why? Well, there's an r here. What does that r mean? It means the distance from a given axis. That means every body is going to have multiple moment of inertias. Many times we will be calculating what we call I sub g, which is the moment of inertia about the mass center. The moment of inertia about the mass center is a special one, but we're also going to calculate moment of inertias about other axes. But each axis is going to have its own moment of inertia because those r's are going to change. Another thing to note is that since we're integrating over an entire volume, now I did a 2D example on my illustrations, but hopefully you can picture it in 3D as well. A little dm, a little piece of mass would be a cube, and we're going to add up all of those cubes, and we're going to be integrating in the x, integrating in the y, and integrating in the z, so we get all of the cubes added up to make our potato or whatever we have that's rotating about. And to do that, we would need a triple integral. We'd need to integrate about the x, about the y, and about the z. Since it is not a prerequisite to this class to know how to do triple integrals, we will instead be using the disk and shell method to solve these integrations using single integration. And I'll show you how to do that in the next video.